I want to take a look at the derivative of the inverse sine, and I want to do it in such a way that I use my knowledge of the derivative of sine in order to find this. Okay, so here we go. I'm going to start with y equals the arc sine, or the inverse sine of x. I think of that as the angle whose sine is x. And I want to find dy dx. I want to find the derivative here. Okay. Now I could go back to the definition of derivative, saying the limit as h goes to 0 of sine inverse of x plus h minus sine inverse of x all over h, and see if I can work that through. It turns out there's a substantially easier way than doing that. And what I'm going to do is I'm going to use implicit differentiation. I'm going to first of all take the sine of both sides. So I have the sine of y equals the sine of the arc sine of x. And what is the sine of the angle whose sine is x? Well, what's the name of the guy whose name is Harry? It's Harry, right? This is just x. The sine of the angle whose sine is x here. Right. So, what I'm going to do now is I'm going to implicitly differentiate. I'm going to take the derivative of the left-hand side with respect to x. I'm going to take the derivative of the right-hand side with respect to x. I'm thinking of y as a function of x. When I'm doing implicit differentiation, I don't worry about having y explicitly written as a function. It's just there's an equation here that if you told me x, I could maybe solve for y. So it's kind of not explicitly defined, it's implicitly defined. So here we go. The right-hand side is kind of easy. The derivative of x with respect to x is 1. The left-hand side, the derivative of sine of y with respect to x. Well, the derivative of sine of y with respect to y would be the cosine of y. But I'm not taking it with respect to y, I'm taking it with respect to x. So the chain rule says multiply by dy dx. Solving for dy dx at this point, I've got that dy dx is 1 over cosine y. I'm going to pause here for a moment to ponder the import of this statement. Over on the side here, I want to note that the derivative of the sine of x with respect to x is the cosine of x. Now I have that the derivative, right, y was equal to sine inverse x. I've calculated dy dx. So the derivative of the sine inverse of x is 1 over cosine y. Derivative of sine x, cosine x. Derivative inverse sine x is 1 over the cosine y. Because the derivative of the inverse function is the reciprocal of the derivative of the function with the other variable plugged in. Okay. Now this answer is completely unsatisfactory because I didn't start implicitly, I actually started explicitly, right? So I don't want my answer in terms of y, I want my answer in terms of x. Now this stage, this step of the problem is different each time we do it with different inverse functions. But what I need to do is I need to get this back in terms of x's. Well, x is related to the sine of y, and yet I've got a cosine of y here. So there's algebraic ways of doing it, but you know, this is a trig function. So when I see trig functions, I really feel like drawing a triangle. So I'm going to draw a triangle in here. I want in this triangle to represent this equation right here, or this one, they're equivalent. But y is an angle, and the sine of y is equal to x. So if I put this right here, with y being this angle right there, and that's a right angle, then the sine of y should be the opposite over the hypotenuse. If I make this an x and that a 1, then this triangle right here gives the same relationship between x and y that either of those two equations does. X is the sine of y, right? Y is the angle whose sine is x, either way you think of that. Okay? But what I see in this triangle now is a right triangle with two sides known and the third side unknown. But boy, I can just use Pythagorean theorem here and get that 1 squared minus x squared has to be, well, square root of that would be that other side. But now I can see, hey, what's the cosine of y? The cosine of y is the adjacent side divided by the hypotenuse. So this is equal to 1 over adjacent side divided by the hypotenuse, which is just 1 over the square root of 1 minus x squared. The net result is we started with y equals the sine inverse of x. The derivative is 1 over the square root of 1 minus x squared. The final result here does not at all look like the statement that I said, where the derivative of the inverse function is the reciprocal of the derivative of the function with the other variable plugged in. That once you've got it back in terms of x's, it doesn't look quite that nice. But right here, the derivative of sine x is cosine x. The derivative of inverse sine x is 1 over cosine y. Then convert it back to x's, and we've got the derivative. Right? I'll also point out on this one right here is that I find this a very surprising result, in that for so many of the functions that we deal with, if you take the derivative of a polynomial, you're going to get another polynomial. You take the derivative of an exponential function, you're going to get an exponential function. If you take the derivative of a trig function, you're going to get a trig function, or maybe a combination of trig functions. But if you take the derivative of an inverse trig function, you get something like this. It's an algebraic function. It's got quotients and squares and radicals and stuff, but it just looks completely different, like a completely different function than an inverse trig function. However, if you take a look at the graphs of things, what's going on here, right? The arcsine function, remember, is this piece of a sine curve that would be going up the y-axis. If I could continue on, I'd be drawing a sine curve up the y-axis. This is what the arcsine looks like. It has allowable inputs from -1 to +1. It has outputs between minus pi over 2 and plus pi over 2. So this is y equals the arcsine. If I look at what its derivative should be doing, it's starting off here completely vertical, right? I want to do the graph of y prime now. It's starting off completely vertical. And then it's got positive slopes the whole time. The lowest it gets down here is to a slope of 1. So like at -1 right here, you're essentially bumping up against a vertical asymptote. Likewise, at 1 on this side, it's completely vertical again there. So the derivative should look something like this, with vertical asymptotes at 1 and -1. Well, I look at what's going on here. The 1 minus x squared's got to be positive, right? So x squared's got to be somewhere between, well, x squared's got to be between 0 and 1. So x is somewhere between -1 and +1. When x is equal to 0, this whole thing is equal to 1. And the closer x squared gets to 1, either with x being +1 or x being -1, the closer the denominator gets to 0, and you're bumping up against asymptotes. This function really does nicely describe that shaped graph. That's what the derivative of this function should look like. Okay. Anyway, there you go.